some literature, some textbook, they use another definition. Yeah, it's not correct or wrong. Okay. But in my opinion, now I separate the motor into types, the biggest one with the DC and AC motor. Yeah, that is the biggest one that I think cover the whole of the motor in the world. The motor use not either DC or AC, just only this AC or DC. That's it. It can cover the whole type of the motor in the world. I'm not sure if has anyone have seen about the movie called The War of the Current. Have you some? No? War of the Current, I think the movie last 5 years ago. Is a movie about the history, about the DC and AC. Because at that time, the guy, Thomas Edison, they proposed DC current. They want to transmit everything in DC. Yeah. In the same time, Nikola Tesla proposed AC. But at the beginning, Thomas Edison proposed DC first. Nikola Tesla come later, proposed AC. He is very genius. At that time, we don't have some simulation tool, but he know in mind how it works when you put AC current into the motor, how to generate magnetic field in the motor. That is very genius how to make it. Even today, we have some finite element method to see what the flux look like in the AC motor. But at that time, can you imagine at the 19th century, something like that, Nikola Tesla know about how to propose the AC to the system. Yeah. But as you know, at the end, the AC system is used as the fundamental for the power transmission nowadays. Yeah. Not the DC. Yeah. That is maybe if you have a chance, you can take a look. What is the idea? What is how they compete to each other to propose DC and AC? Yeah. But come to our lecture. So we also have DC and AC also. And I can say that for the electric vehicle, for the DC may be obsolete for power station. Now we don't use DC motor anymore for electric vehicle. Yeah, there are some drawbacks, the big drawback for the DC motor, but actually there are some benefits also. Yeah, but now with our powerful motor controller, so to control AC is you can get higher efficiency, higher power density, robustness, everything. So that is why AC motor play an important role for the electric vehicle. By the way, we need to talk a little bit about the DC just to give you overview how it works. Yeah. As I mentioned in the beginning, when I was young, when I was child, I played with the DC motor with the toy. Everybody play with this small car. It's a Tamiya motor. At that time, it's the expensive one. At that time, if you have this kind of, the motor is more powerful than the normal DC motor. Yeah. And when we talk about the DC motor, just take a look how it looks like. Maybe this slide just the new one. So we can see about some structure of the DC motor. Yeah. The motor actually consists of two main parts, stator and rotor. That's it. Stator actually consists of the laminate steel, copper, and in this case it consists of magnet. Here, N and S, permanent magnet here. So for the DC motor, we have two main types. We say that the PM field and wound field. PM, the name is a permanent magnet field. It means the field generated from permanent magnet. For the wound field, it means you need to generate magnetic by using the wire, not permanent magnet. You see, it's no permanent magnet here, just only the wire. And the wound field stands for you need to inject current into the coil to generate magnetic field. That is the difference between EM field and wound field. Yeah. When you see closely about the structure of the DC motor, you have the stator here outside, the same, similar, and it's made of the ferromagnetic material like stainless steel. You have the magnet for the PN field here, A and S. For the wound field, you have the coil, and you inject some field winding, field current here, IM, to this coil, to the stator coil. Stator is really stand still, it's stationary part, stator. For the rotor, it means it's rotating. Yeah. For the PN field, the rotating part is in the middle. We call armature. And this coil called armature winding. And we need to put some current into armature winding to generate the magnetic field. As I mentioned how to generate magnetic field, there are two ways. The first way, use permanent magnet. They can generate magnetic field by themselves. The second way, you just put the current into the coil and then they generate magnetic field also. Yeah. What's the difference? The difference is for the permanent magnet, when they generate magnetic field, they generate constantly. Not concerned about the current anymore. If they can generate 0.5 Tesla, they generate 0.5 Tesla. Yeah, that is the property of the magnetic field. But for the wound field, the benefit is you can adjust the current into the winding here, and then you can control your magnetic field by control this field current. You will see what the benefit later, why it's very important to control the field, the magnetic field. Yeah. Because it will reflect to your motor performance. Yeah, if you can control the field, you can run at very high speed. With the magnet, if we cannot reduce the field of the magnet, so the operating range, the speed will be decreased. So that is why that is the one benefit that we can get from the field with the current control here. So can you imagine the rotor in the center? And usually the rotor will be rotated, will be moved. How can we supply the current into the moving part? Yeah. If you want to supply the current into the moving part, you need to have some trick. Yeah? Because you cannot put the wire into the rotor, because rotor will be rotated. So that is why for the DC motor, they need another component to transmit the current from the source into the rotor winding or the armature winding here by using brushes and commutator. Yeah, brush and commutator. That is the two important components for the DC motor that you need to take care of. If you cannot supply the current from this source to the winding of the rotor or the armature winding, your motor will be dead, cannot work anymore. That is the biggest drawback of the DC motor, because they need to take care for the brushes and for commutator. Unfortunately, usually these two parts will be wear out very soon. However, in the past, for the DC motor, Usually we run maybe 1,000, maximum 2,000 or 3,000 RPM. Okay, the brushes is well, but okay, it's not so fast. But today, for the motor in the EV car, you know how many RPM that is run for the motor nowadays? It's up to 20,000 RPM. Can you imagine? Motor spin at 20,000 RPM, and how can brush and commutator can resist about this. So that is why for the modern motor for the EV, we don't use the DC motor anymore because of the brush and commutator. And when we want to build this kind of the motor, it will take some part, some space to put the brushes and the commutator also. That is why DC motor is a little bit larger. It's not good for the electric vehicle application because we want to have it compact. So the two disadvantages of the DC motor, that is why we don't use in the modern transportation anymore. Yeah. And the same for the valve field, for the armature is similar. They also need the brushes and also need the commutator. Yeah. That is the principle of the DC motor. If you remember, for the Lorentz force at the beginning, I talking about. See, you have the magnet here, N and S. You have magnetic flux flow from N to S. And then you have the conductor here, and you put the current into the conductor. And when you put the correct direction of the current into this conductor, that means the force will be generated, and this force will move this rotor. That is the principle how DC motor works. It's based on Lorentz force. Yeah. This one. Okay, and can you combine between the principle of the force and then apply to this kind of the motor? Yeah, how it works. Yeah. And when we talk about the PM field and valve field, this graph really interesting. As I mentioned, for the PM field, we cannot control the magnetic field of the magnet for the DC motor. That is why when we torque right up here, the torque constant here, power right up here, after a certain point at the rated speed. So when you cannot control the magnet or you cannot control the magnetic field, the power will drop immediately. That is the drawback of the PM field of the DC. That means your operating speed will be narrow. In the opposite, for the valve field, as I mentioned, the valve field you can control the field by controlling the current into the field. That means when the motor runs to a rated speed and the power go up to rated power, they can keep constant power in this area, because in this area you can control or you can reduce the flux, the magnetic flux of the field winding. When you reduce the magnetic flux, that is why this area we call field weakening. Field weakening. That means you need to reduce the amplitude of the magnetic field. With the PM, we cannot do it. But with the valve field, we can reduce or we can control the field current. That is why we can prolong or we can work at the higher speed. As you see, for the PM field, maybe the speed is very narrow. For the valve field, you can extend the operating speed until this point. Yeah. That is, you need to trade off between PM and valve field. PM field maybe you have more compact, But for the valve field, you need to put some winding, so it's a little bit larger. But the benefit is you can control the field easily. Yeah, that is the characteristic of the beam field and the valve field here. And when we compare with our four quadrant that we talked at the beginning, so how it works with the DC motor. In the first picture, we call forward motoring. It means, can you remember, it works at the first quadrant, forward motoring. That means the torque, positive, speed, positive, and power is positive. So in this one, the rotor rotates counterclockwise, counterclockwise rotate in this way, and then the current feed from armature current in this direction. That means it consumes the current from the source to the armature winding. So that is why it's located in the first quadrant here, and it works as the forward motoring. At the same time, for the reverse motoring, you see the direction of the rotating is in another way around, in the clockwise here, and the current comes from the armature winding to this area. That is why it comes to reverse motoring. For the generator, it will be the opposite. For this one, the current will go back, this means to brake, and this one, current go back, this will brake also. And this one, current comes from the source back to the armature winding. That you can map between four quadrant operation with DC motor. As you can see, it's very easy to control the motor forward and backward. Just change polarity of the current, and then you can work in four quadrant easily. That is the benefit of the motor. As I mentioned, you don't need to have the gear, just change the direction of the current. And for the AC, we just change some control of the current. We can change the mode easily. That is the idea how to use the motor for the EV. So, for the DC motor, at the moment I say that we don't use for the powertrain anymore, but they still use in the wiper, for example. This example from Toyota wiper, they still use the DC motor here. As when you see closely here, the brush is here. Brush is the black carbon here, and you have commutator here, just to connect to the wire here. Because when you put the current from outside, it will be passed through the brush and then through commutator, and then go to the wire, onto the wire here. And here is the magnet, N&S, and then here is a laminate steel rotor. You can see the DC motors still used in the vehicle, but not the powertrain. But they use for some accessories like the wiper, the mirror, the door, when you adjust the light, if you have the motor inside, they still use DC motor because it's very easy to control this kind of the motor. Just regulate the voltage, and then you can control the speed of the motor easily. For the AC, a little bit complicated. So that is why for the simple device in the vehicle, they still use the DC motor. In the last month, actually, I just got some requests from car manufacturer. They want to test the mirror, the motor that used for mirror adjuster on the door. So that is why we still use the DC motor in automotive. Now I come to the big part of our lecture today for about AC motor. Yeah, there are a lot to talk about AC motor. So just go step by step, and maybe today, as I mentioned, maybe I don't go to mathematics so deep. Just give some the idea and then the principle how it works, and hopefully you can explain that when we talking about this motor, you know how it works, how it can rotate it. Yeah. So before we start with the type of the motor for the AC, I would like to mention something about rotating magnetic field. Yeah? It's really important behavior or phenomenon that occur in the AC motor, and it's like the magic how it works. Okay, when we talk about rotating field, what do you have you imagine what it is? Just imagine that you have permanent magnet, and this permanent magnet can be rotated. That is the idea of rotating magnetic field. Usually when we have the coil, when we put the current into the coil, it will generate magnetic field, but this magnetic field will be stand still, will be stand as it is. In this case, when we put the current into the coil, it generates magnetic field, and this magnetic field can rotate. That is the fascinating behavior. And as I said, Nikola Tesla know about this. Even they don't have the simulation, but in his mind, he knows how it works. As I remember at that time, Nikola Tesla put the idea of Nikola Tesla, they use only two phase to generate magnetic field. But in present, at present, we use three phase. Commonly we use three phase for our system, to generate the rotating magnetic field. Let's take a look about this behavior. We have the stator here, and we have the coil A, B, C, B, A, C, and you see A is here, C is here, and B is here. Yeah. As I said, usually when we see this simple, we have the dot and we have the cross. What the meaning? The dot is the current come up. The cross it means current go inside. And usually when current come up, it will generate something like the magnetic field. Yeah, we use the right hand rule. Yeah, when we just use this type. The dot here, for example here, that means it will generate some flux here in this direction here. Here, this direction or this direction. Come up and then just screw it. And for this one, come up and just screw it. So this one will generate a flux in this direction. Yeah. And then from you can see the flux will become in this case. When we combine it together, it's similar. This one is come up. This one come up here. You see, A is put from. We take a look only the first coil. We have A here, dot, A plus, A minus. Yeah. When it come up and then we go in this way, that means we use right hand rule So we have flux in this direction. That is why it's defined by N to S. It's N and to S. As I mentioned, this one we have one pole, yeah, N to S. That means one pole pair. It's a two pole now. Yeah. For this one also, for this stator coil, when we arrange this stator coil, when we inject the current into this coil, we can generate the magnet in the coil. It's like the magic. Like when you put the current here, you generate the magnet. It's called electromagnet. The magnet generated by current. Yeah, that is the idea. But the interesting thing is this magnet don't stand still. They will move with the speed omega. For example, if we put the current with some frequency, this magnet will move along the stator. Yeah. And for this is the example for the two pole. Yeah, two pole here is a one pole pair. And for the four pole, it's similar. You have NS, NS, and then you have four magnet. And four magnet will rotate when you inject the current into the coil. And for the H pole is something like this. Imagine this just only the stator coil. We don't talk about the rotor yet. Rotor is in the center. Yeah? Rotor is in the center. It doesn't matter what the rotor look like. Now we focus on the stator. So the conclusion, when we have this kind of coil, when we inject the current, we generate the magnet. And this magnet can rotate according to the frequency that we put into the coil. This is the idea of the rotating magnetic field. Why this behavior is very important? This behavior will explain about how each motor works for the AC motor. Now we talk about AC motor. And AC motor, they use rotating magnetic field as the principle. So, how about the three-phase winding in the AC motor? At this time we say, okay, that's only one coil here. One coil. And if we define this coil as the phase A, and the angle 0 at the beginning, and then we put another coil, let's say 120-degree shift from the first coil. Here, you can see this angle is 120 shift from the first one. And the third coil, another 120-degree shift, which means 240-degree shift from the phase 3. So you have phase A, phase B, and phase C together. Now we're talking about three phase. Yeah. For this example, just only one phase. Yeah. But now we're talking about three phase. That is commonly used for the electric motor in EV. We use three phase. And motor in the industry also use three phase, because we have the three-phase supply. So that is why we are talking about the three-phase. So when we link between the structure of the coil and then the definition of this coil, yeah, phase A, phase B, 120-degree shift, and phase C, another 120-degree shift from phase B, yeah, and it's 240. When compared with phase A. So, how it works? Now when we talking about the magnetic flux density of phase A, yeah, we focus on this one, phase A. Let's see. As I show in this figure, when we put the current into this coil and this coil, we have this kind of the magnetic flux pass through this one, and when we plot the magnetic flux in the theta is the rotor position. At theta 0 here, theta 0 here, we have the maximum magnetic flux here, and then when it theta move, you don't move here, but you just this one just like when you stand at this point and then you move yourself pi over 2, it means 90 degree pi over 2. That means you don't stand here anymore. If I draw this picture, so at theta 0, you stand here. When you stand here and you see the magnetic flux, you see the maximum flux density. When you move from here to here, theta 90 degree, when you look at the magnetic flux here, is the magnetic flux here. It comes in the opposite way. Yeah, this one when you move to here, and then when you move to here, and then move here, and then move back to here, you can get this relation. Yeah, this one just to show about the simulation when you use the finite element method. When you define the position of your observer, you can see about the magnetic flux density of the motor by varying the theta here. And when I put together in three phase, yeah, it's just only one. When we put three phase together, you see the relationship between the flux density of A, B, and C. And then when we combine it together, we can get this kind of magnetic flux density for this three-phase machine. But this picture just take a look at it, because there are so many mathematics inside how to calculate this kind of graph, but I don't go in detail. Just give some feeling when we have the three-phase winding. That means you will have this kind of behavior or phenomena. You have flux A, B, and C, and then when we combine together, you have the flux S, flux density S. That is for the three-phase magnetic flux density. Or maybe in the exam, someone can draw this kind of graph. I think it's more complicated. Yeah. So, this is another mathematics. We call the space vector. When we talk about the space vector, it means you need to imagine the vector will be go in the space. Yeah. For the three-phase current, you have this kind of the graph. You have to see some sinusoidal IA, IB, and IC. IB will shift from the IA 120, and IC will shift from IA 120. Yeah? And then when we use the mathematics, you see this is the reference A, reference B, and reference C. At the theta 0, that means theta 0 here. What you see? Theta 0 is mean IA equal to the maximum 1, IB and IC equal to minus 0.5. Yeah, 0.5. That means when we draw the vector, so we draw at first phase A, the length here, and then phase B, it will be shifted according to this axis B, IB, and then because now you see we have positive A, here positive A, it is better to draw here. So at theta 0, what do you see in this graph? Theta 0, phase A is the maximum amplitude, now is 1, for example. So let me draw this phasor IA, this line IA. And at the same time, you put also current into phase B. But phase B, what do you see? It's a minus 0.5 minus. Here, positive minus in this direction. When you draw IB in to connect just from IA, and then you draw the vector, we call the vector diagram here, but it's a minus IB, minus 0.5 IB. If we draw in this way, and then for the C, it's also minus 0.5 IC, and for minus C is in this direction. If you go back in this direction, it's a minus 0.5 IC. You see, you have IA minus 0.5 IB and minus 0.5 IC. Because minus C is in the direction, minus B in this direction. When you draw it together, you get the final IS. That is why you get this IS here. Just only the timing at theta 0. Yeah. So when we move, to the second state, is a theta pi over 2 or 90 degree. Let's see how it looks like. We have the same vector A, B, C. So at this state, what is the pi over 2 is here? Pi over 2 here. Can you see what the meaning here? At pi over 2, what is the phase A? Phase A here. It's come to 0. That means IA, you don't have anything like this. You don't go any direction because it's become 0 here. Yeah. But for the IB is this graph. IB here, IB is this graph, is positive. It's a 0.8 something. Yeah, or somebody can help me to calculate what is the cosine 120, cosine 120 plus 90. Okay, somewhere here, let's say it's the 0.8 something. So IB plus is plus, plus. That means IB will be here. It's a 0.8 something IB in this direction. And at the end, you have minus C. Minus C is in this direction. Minus C. That means it will be here. C minus 0.8 I see here. So at the end you draw this curve. Actually it's 90 degrees here, but maybe my drawing is not good. But at the end you should get this curve because the amplitude here and here equal, yeah, from this diagram. And you see at theta equal to pi over 2, the current move from this to this. Yeah. That means, as I said, current generates magnetic field. At this time, at 0 degree here, it generates a magnetic field in this direction. But now at the pi over 2, it's moved from here to here. That means it's moved from here to here. Here pi over 2. Delta equal to pi over 2. That is why we call rotating field. Because it's rotate from this one to this one. And when we go further to pi, for example, you will get the result like this. That means if you move from this to this, and then go further to this. And that's why if you move in circle at the end with the frequency omega, yeah. When you can understand this behavior, that means you can understand what is the rotating field work in electrical machine. As I said, for AC electrical machine, it generates magnetic field with rotating. It's not stand still. That is the behavior why it rotates. Yeah, why inject the three-phase current, and then you can get the result of each current, and then it will be rotating. Yeah.
The rotating magnetic field is happen on a stator.
On stator, yeah, exactly. Now it's only on stator. We talk only on stator because the winding is on the stator. Yeah. And later I will show how it interact with the rotor. Now just understand the principle about rotating field. Yeah. This may be one question to explain about this behavior, but maybe I will shift this graph a little bit. Yeah. If you understand this one, you can plot this vector easily. Yeah. Hopefully you now understand rotating field about the model. Yeah. Because when I watch the study, it's very difficult to understand how it works. Yeah. At the end, it takes time to understand how it works. So that is why today I would like to share about how it works. I think it's very easier to see how it works now. Yeah. But if you don't go to mathematics, just imagine when you put three-phase current into the stator, it will generate the magnet, and magnet will be rotated. Yeah, that is. Yeah. But it's the reason behind is from mathematics, just to prove why it is rotated. Okay, now you understand about the rotating field, and then when you see some motor, another configuration you need to understand is how they connect. Yeah, because now you have 3 wires, for example. How to connect? You have here 1, 2, 1, 2, 1, 2. Yeah, before phase A, B, C. Some guys say about delta or star. Yeah? There are 2 configurations, star or delta. Star, very simple. Star is mean just join some terminal together, and then you call it terminal N or neutron. That is the star connection. For the delta, just connect one to each other like the triangle here. We have A plus A minus, C plus C minus, B plus B minus. There are two possibilities to connect this wire. Usually, the motor in EV, the motor manufacturer already connect for us. So we don't know how they connect usually because it's already in the housing. If they don't tell us about what configuration, it's not easy to check what is the star or the delta. But for some application like the motor in the industry, sometimes they provide us 6 terminals, and then we can connect by ourselves. We want to connect in star or we want to connect in delta, is up to you. But for the EV, usually they connect for us. And do you know what the difference between star and delta? Not just for the fancy or for the beautiful schematic or something like that. Actually, when we talk about the star and delta, it's some simple formula for star and delta configuration. If you connect in the star, just know that I call I line equal to I phase. I explain later what the line, what is the phase. And V line equal to square root 3 V phase. That is the star. For the delta, I line equal square root 3 I phase. And V line equal to V phase. Yeah. Different. And what the meaning? What the line? What is the phase? So when we connect star, for example here, it's a simple configuration. A, B, C. And if we distinguish this one, when we see the line mean is here, it's an I line. I phase meaning is here. Phase meaning is go to the point. But for the lines mean just the line, just go from outside to this one. That is the definition. That is why for the star, I line and I phase is equal. But for the V line and V phase, V line is mean V between this point, and V phase is V in this point. That is what the definition of the line and the phase here. For the delta, here also I line and I line both I phase here. You see, I line is not equal to I phase anymore, and because the I line come here, they need to split up into points. So that is why I line is not equal to I phase anymore. But for the V line, here is still equal to V phase here. That is why V line and V phase are equal to each other. That is the fundamental that you should understand when you talking about star and delta configuration. However, based on my experience, I found that the motor that used in electric vehicle usually they connect in star. I found some motor connect in delta, but not too many. Yeah, that is, we say that usually the star connection is preferred for electric motor in the EV. Yeah, for the delta, the benefit is maybe you can use the low voltage, but for the star you need a little bit higher. Yeah, that is the idea about the star delta configuration. It's the electrical fundamental. Yeah. Maybe in the quiz there are some questions about how you calculate the power by using this kind of the configuration. Yeah. Okay. Yeah, but I don't write it yet. So maybe there is a little bit more in detail to calculate the power, because power is equal to I multiplied with V. Yeah. But now you have something like the phasor. You have the current, you have the voltage not at the same angle. That you need to concern about the phase shift between voltage and current. Yeah, but not in our topic at the moment, but just to understand that for the motor you have two configuration, star or delta. Yeah. Okay, now just come with the first type of the AC motor. The first one we will talking about asynchronous motor. So for the AC motor, I separate into two types, asynchronous and synchronous. If you imagine, the name already clear. Asynchronous means it's not sync. The simple way to say it is not sync. What the meaning is not sync? When we describe the synchronous, we define based on the frequency we put into the motor. If the motor rotates at the same frequency with the input frequency, we call it synchronous. For asynchronous, it means the rotor rotates in different speed compared to the input frequency. If you know, in our power system, we have frequency at 50 Hz. Yeah, with our electricity, we supply with 60 Hz voltage to 120 volt. Yeah, that is our power system. So, if we put the motor plug in direct to our grid. Our grid is provide voltage frequency at 50 Hz. That means this motor will rotate at, if the synchronous frequency is made, it needs to rotate at 50 Hz also. But somebody said, why? You say that you cannot connect direct to the grid, because otherwise the motor doesn't work. I say that it doesn't work for the motor that you want to control the speed. You want to control current. You cannot connect direct to the grid. But in our conventional system or in our industry, Usually we have some kind of the motor direct connect to the grid. And if we run at a certain speed, the problem is we cannot control the speed easily. Yeah, because if you say that the speed, the F equal to FOP, if we have the fixed speed, how we can control the speed? How when we fix the frequency F is constant, how we can control the speed? That means we need to control the pole. It's not easy to control pole, yeah? But in the past maybe there are some trick they can generate more pole. But now we don't do this. Yeah? Or if we want to control speed, we cannot change the pole. That means we need to control frequency. If we want to control frequency, that means we cannot connect direct to the grid. Yeah, that is the point. Because in the EV, we don't want to run at a certain speed. We want to run faster, slower, depends on the traffic or something like that. That is why in motor, we need to control the speed. We need to control the frequency. That is why we need inverter. But for the grid, if we connect with the frequency, certain frequency, that means the synchronous speed of this motor will be 50 Hz. For asynchronous motor, as I said, asynchronous is not sync. That means this motor will rotate at frequency not equal to 50 Hz. It's maybe 49, 48, 40, depends on the load. But of course not 50 Hz. That is why the name comes from asynchronous motor. Yeah. I will show you later why they cannot run at synchronous speed for induction motor. That is the behavior that you need to understand how it works for induction motor. If you look, it's very simple. Just plug 3-phase to the terminal and the motor will rotate it. I say that for the induction, it's easy to make it run,
คะแนนไฟฟ้า
but
จะปล่อย
it's
มา
difficult to control.
เขาบอก
For synchronous, it's difficult to run, but it's easy to control. And you will see the meaning later why it looks like that. But now just understand for asynchronous motor, when we put to the grid like 50 Hz, you cannot run the motor at 50 Hz anymore. That is the behavior of induction motor. So how it look like? So we go step by step. How to generate torque from induction motor? Why they call induction? That is the meaning. Do you know why it's called induction? Do you know in induction heat, when you go to some restaurant, there are some induction heat. Yeah, that is just, it's like the induction device. They want to induce some heat to your pot. Yeah, something like that. The induction is mean to induce. Yeah, that is the meaning of the induction. So, what the behavior how to make it turn is explained by this picture. So before we go to this picture, we see about the structure of the induction motor first. So just make it clear. For induction motor, another name is asynchronous motor, because I have seen in some advertisement, for example, for the Tesla, they show that the motor is the asynchronous motor. When some guy read, oh, what is the asynchronous motor? It's not familiar, but actually it's the induction motor. Just the name, something like that. So the structure of the induction motor is simple. The stator, we're talking about it already. We have the coil here, phase A, phase C, phase B, blah blah blah. We have how many slots? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 12 slots. Now we say that we have 12 slots here for the stator. Stator is similar for asynchronous and for induction and DC is similar. You can use the same stator. The difference is only the rotor here in the center. You see, the rotor here you have is rectangular. We call it the copper bar or aluminum bar. It depends on your how to produce, how to manufacture. Yeah. For the low cost induction, usually we use aluminum bars. Yeah. For high performance induction, they use copper bar. For Tesla motor, the first generation, they use induction with copper bar. Yeah. That is, Tesla claim that you can get higher efficiency with your copper bar here. Just replace aluminum with the copper. Yeah. And they claim that efficiency will become higher. Yeah. And this is the bar here when we cut, and we see here the bar here, a bar. We put only one pair of the bar, for example, in this bar and in this bar. And then we have bar here. We just remove the steel. We just bring the bar here. Yeah, we have bar in the top and in the bottom. And at the end, it's interesting. You have the end ring. You see later, or maybe I show some picture here. End ring. End ring is here. Is to make each bar short together. We call end ring. At the front, at the rear, we have both end ring. And here we have roller bar here. Yeah, similar. So come back to this picture to explain the behavior of the induction. When we have the bar here, and we have the end ring here, what do you see? Do you remember when we put the three-phase current into the stator, they will generate magnetic field, and this magnetic field will be rotating. You remember that? Magnetic field rotating. This spin of magnetic field. When the magnetic field rotating, and when you have the rotor bar here, that means at the time 0, when the bar at the standstill, the magnetic field will move. When the magnetic field starts to move, they cut the rotor bar. And for example, we have the bar here, and if we have magnetic field NS, and then this magnetic field will NS. When this magnet moves, this magnet will cut the bar according to Faraday law, as I said. When you have the rate of change of flux of the conductor, you will generate the voltage. Just go slowly. First, the bar stands still, the magnetic field start to turn. When it starts to turn, this magnetic field from the stator, from the stator, cut the rotor bar. When it's cut rotor bar, according to Faraday laws, it will generate the voltage. That means it will generate the voltage across this bar. What happens next? When it generates the voltage of the bar, when you see it's like a resistance, because the bar will have some resistance usually. And when you have the voltage across the resistance, what happens? You have I flow into the bar. That means it will generate the I bar here. When it generates the I bar here, this I bar will, according to Lorentz force, you have I, you have B, you can have F. That is why this bar will be moved. Yeah. Repeat again. You have the rotating field at the center. When rotating field starts to rotate, it will cut the bar here. When it cuts the bar, according to Faraday laws, it generates the voltage. When it generates the voltage, the bar has the resistance, and then you short each end together. That means you have the closed loop here. That means you have the current flow into the bar. When you have the current into the bar, you have the magnet rotating. That is why you have the F. You have force. That is why it makes this motor turn. That is the behavior. Yeah. How to explain how it works. Yeah. And as I say that, this one must be asynchronous. Why? Just imagine if this bar rotates at the same frequency of magnetic field or rotating magnetic field. That means the magnetic field cannot cut the bar anymore because it will run together. For example, if we have some prime mover to run this motor at the same frequency at the speed of the rotating field, that means the bar cannot cut by this magnetic field. When it cannot cut by magnetic field, they cannot generate voltage. They cannot generate current, and then they cannot generate force. That is why if it runs at the synchronous, this motor can work. It works only the frequency of the rotor different from the frequency of the rotating field. That is the idea why we call asynchronous motor. Yeah. I think it is the fundamental of induction motor how it works. I don't go to mathematics, but just explain to understand the behavior, yeah, how it works. Yeah, that is the phenomenon behind this motor. Maybe today we stop with the induction. I come